Alright, so this is the topic 1 review, which is going over all of section 1 to 1.4, which we went over like in about 2 weeks. So let's get started. So 1.1 was talking about relations and functions. Know that relations and functions are, let's start with relations. Relations are talking about any like set of data. And this is at least two order pairs, like so. A function cannot have repeating x's. Yes, no repeating x values. So, question 1. Determine whether the relation is a function. Find the domain and range. So, you have 10, negative 10, 6, 5, negative 6. So this is, yes, this is a function. And the domain would be 10. I want to put this in order, actually. So it would look like this. Negative 10, negative 6, 5, 6, 10. And the range would be my y values, which is 2, 2, 4, 3, 7. So 2. I only need to write 2 once because 2 has been repeated. And it's okay if my range is repeated or my y values are repeated. It still doesn't affect the fact that it is not a function. So 2, 3, 4, 7. Nice. Pretty easy. Let's look at the graph right here, number 3. So we have, what is it? 1, 2, 1, 2, 3, 4. This is 4, 0. Use a different color because it's hard to see. This is 4, 5, 6, 7, 8. 8, negative 1. This is 1, 2, 3. So 0, 3. This right here is 1, 2, 4. 2, 4. This is 1, 2, 1, 2. 2, negative 2. This is 1, 2, 3, 4, 5, 0. 5, 0. Okay. So, is this a function? And this is not a function. Because the vertical line test right here. What the? This vertical line test right here. It fails right here. It fails here and here. There's 2 of them. So this is not a function. Okay, let's talk about a domain. So, this is negative 8. Negative 8, 4, 0, 2, 2, 5. And for this one, like, I do want to repeat them because it shows that it is not a function because of it. And this is negative 2, this is 0. Oh, negative 1 first. Negative 1, 0. I'll just write all of them. 0, 3, and 4. Not too bad. Elementary stuff for you now. Alright, number 5. Find f of negative 2 and f of 3 for each function. So I'm going to do this one. So what this is saying is that when x equals to negative 2 and when x equals 3. So I'm going to have 2 answers. So f of negative 2 is equal to minus negative 2. It's not written well. Minus negative 2 plus 4. So minus times a minus is a positive. So it's 2 plus 4, which is f of negative 2 is equal to 6. So I evaluated what when x is equal to 2. That's what the question is asking me for. So I did one of the problems, or half of it, because this question is asking me for both negative 2 when it's equal to x, or when x is equal to 3. So I'll just draw a squiggly, and f is equal to 3 is equal to negative 3 plus 4. You see how I put the parentheses? That's because this x right here has a parentheses, like imaginary parentheses as well. So negative times 3 is a negative 3 plus 4. This is a positive 1. So f of 3 is equal to positive 1. Not too bad. So attributes of functions. So this is another thing that we talked about in section 1.1 and throughout like really all of section or unit 1. So find the domain and range of each function. State the domain and range using interval notation. So let's look at 7. 7 has like this weird looking equation, and it looks weird because I need it to turn into y equals mx plus b. So to do that, I need to move everything away from the y. So I'm going to move the x, which is minusing x on both sides. So it becomes 3y is equal to negative x plus, minus 1. When I do this, I still have a 3 next to my y, and to get rid of it is to divide everything by 3. So then this will turn into y equals to negative x over 3 minus 1 over 3. Okay, but I'm not done yet. Right? Yes, I'm not. Because the question is asking me to find the domain and range. The domain and range, this is a linear graph, right? Because you know that there's no power in there, and you know that the x is just whatever. And if I graph it, let's go to Desmos. Oops. Go to Desmos. I can type in this graph right here, like this. Negative x over 3 minus 1 over 3. So look at this. This graph is linear, as in it is a line. So I know, because of the principles that I learned, and Mr. Hong told you, is that all linear has domain, all real numbers for domain and range. So my domain is going to be negative infinity to infinity, and range is going to be negative infinity to infinity, because it is linear. So just understanding the concept behind linear to domain and range. If you didn't know that, you can still check it by looking at this graph and drawing your compass, which I taught in class. You know that it goes diagonal this way, and you know it goes diagonal the other way, the opposite way. So it'll hit every point in the range and the domain. But let's look at this one right here. F of x is equal to negative x squared. So this is already in like my parent function, which is y equals to x squared. So this is already true. I can put this in my calculator because my y is alone. So if I put it into Desmos, y equals x squared. It's the blue graph, which is pretty much showing above. And I know that this graph can go. I could do this. I can make a table. And let's say, for example, I want my x to be like a big number, or a small number, I guess, a negative number. I know that there's going to be a y value. So I know that my domain can be infinitely big and it can be infinitely small. So my domain is still going to be all real numbers, which is negative infinity to infinity. But what about my range? If I look at my range, I can see that my range doesn't touch the negative side. Like my blue graph doesn't touch the negative side. So my smallest value is actually going to be y equals to 0. And that's equal to 0. So we know that interval notation, we use equal or like include as a bracket, but we know that it can go as high as forever. So we can still put this as infinity, or yeah, positive infinity. Note, keyword note. Infinities use parentheses. I don't know if I spelled that right, but you know what I mean. We use parentheses because we cannot quantify infinity or negative infinity. That's why we use parentheses, because we're saying that we're including when we use brackets, but we can't include infinity because we don't know the quantity of it. Nice. Pretty simple for page 1, right? So let's look at page 2. Find the minimum and maximum values of each functions in a given interval, if each value exists. So between 2 to 23, what is the maximum and the minimum? Know that the min and the max, we're talking about y values. And these right here, these are x values. So if I graph this right here in Desmos, let's just get rid of these. Y equals x to the power of 3. And between 2, right? 2, which is here. 2 and 23. So I could put a table, right? And I want to delete all these. Get out of here. So what if I said to 2 and I said to 23? Looking at the behavior of this graph, I'm thinking, oh, it's just going infinitely up forever and ever, right? So even if I go all the way up, I can see that the graph is going infinitely up. So I know that 2 is going to be my smallest value, which is 8, which shows me my y value right here. So my min is going to be 8, or you can write it as an ordered pair, which I recommend because it has more information. It won't hurt you. And your max is going to be, well, what is 23? 23 is 12,167. So what was it? 12,167. Or 23, 12,167. Like so. Not too shabby. Describe the symmetry of each graph. Then state the domain and range using inequalities. So I have this graph right here, right? And I know that the line of symmetry, or if I cut this in half and it's equal, I can cut this graph in half here. I'll use a line. Why not? I'll use a line. I'll cheat. Like so. So what is that that red line? How can I write that as an equation? I can write that as x is equal to 4, because no matter where my point is, like right here, like if I draw any point in this, these are all going to have the value of x equal to 4. Okay, what about the domain and range? The domain, I can infinitely go to the left and I can infinitely go to the right, even if my diagonals look like this. I'll still go to the left and to the right, right? So my domain is going to be still negative infinity to infinity. But what about my range? It's going diagonal northeast and northwest. So I'm only going north. I'm not going south. So My range has to start from somewhere and it ends to infinity. But where does my range start? In the picture, I have to find the lowest point in my graph. So in my graph, I know that it is here, which is y equals 1. So I'm going to actually include it because this graph is solid dotted. As in, if my graph was like this, like dashed, then I would not use a bracket. But in this case, it is solid, so I will use it like so. Function operation and composition. Let f of x equal negative x plus 1 and g of x equals x squared plus 2. Perform the function operations to find, and then find the domain. So for this one, I'll do the right side this time. I'll do the evens. So x squared plus 2, because this is g of x, minus, and I have to put a parentheses for subtracting, negative x plus 1. So whenever I want to do this, I have to distribute this negative sign to flip the signs of all of these. X squared plus 2 plus x minus 1. I can only combine these two right here. X squared plus x. 2 minus 1 is positive 1. And I will actually write is equal to g of x minus f of x. Not too bad. I hope. It is a review. But let's look at this one right here. Like, this equation has negative x plus 1 divided by x squared plus 2. But this is kind of scary, and it can be. But can I factor this x squared plus 2? You could, technically. This 2 could be 2 and 1, or negative 2 and 1, negative 2 and 1. Yeah, you can't simplify this. But okay, let's say that this is my final answer. But this question is asking me for the domain. But the domain, this domain right here is all real numbers, which is the same as negative infinity to infinity. But look at this one. We said that we can't do number divided by 0. This is not allowed. This is not allowed. Yeah, I'll just write here. Not allowed. So we're pretty much saying that x squared plus 2 cannot equal 0, right? So that if I solve this, then x squared cannot equal negative 2. And I square root this. So x cannot equal the square root of negative 2. But we know that in we can't take a square root of a negative square root, and we're going to be learning that next, like, throughout the semester. But just know that this is the same as x cannot equal 2i, and that is just a preview of what we're going to do in the future of the lesson, or in this year. But yeah, page 2, not too bad. Page 3. Determine whether each pair of functions are inverse using function composition. So this is 1-4. And we have two equations right here. And I have to use f of g of x and g of f of x. So I'll do Which one looks harder? I'll do 26. Why not? So remember, step 1. Write outside equation. So I'm going to do f of g of x here, and I'm going to do g of f of x here. And since this is a review, you can always watch like my 1-4 video, which is the last problem. I'm going to be doing the exact same steps, but just a little faster. But first, I need to draw my arrow keys. You should also draw these. All right, let's do the left side first. So f goes, or g of x goes inside f. So I know that I have to write f because f is my outside equation. So x squared plus 9. I'll write f of x is equal to f. F of x is equal to x squared plus 9. But if I replace this x with g of x, which is my next step, step 2, replace x with inside equation. If I make this f of g of x, that means that I have to replace this x as well. And g of x is square root of x minus 9. I'm run out of space, so I'll use it here. X minus 9. And remember, everything that's black in my problem above will still be black, like this. Okay. Now, all we gotta do is simplify. Oh, I guess I should draw this purple arrow. This x turned into this equation. And because we know that g of x is equal to square root of x minus 9, I just substituted it. I could have wrote g of x inside here, but meh. It's just like buffer. It's just like a training wheel. So I just transferred it completely into square root of x minus 9. So if I simplify this, I know that squares and square roots, they're inverse of each other. They're opposites of each other. So what really happens is that these two cancel. So it's x minus 9 plus 9. And this added together cancels, right? So f of g of x is equal to x. Let's do the left side, or the right side. So I'm going to write my outside equation, which is g of, oh my god. G of x is equal to square root of x minus 9. So if I want to make this g of f of x, I need to set this equal to, and you see how this, like if I label my x's like in red, everything in black on the right side of the equation, I have to write it exactly like so. So square root and this minus 9 are going to be in black. But this red, I can replace this x. I'll do it this time. I'll replace it as f of x. So my x became f of x. So g of f of x is equal to square root of, and I know that the f of x is equal to this equation right here, so I'm going to replace it, which is x squared plus 9 minus 9. And this is right here. Alright, so we can drop these parentheses, which I will do. And what's 9 minus 9? That's 0. So really this simplifies to square root of x squared. And I know that the square root and the square, these cancel out as well. So g of f of x is equal to x. We talked about this in 1.4, part 2, where we said that if f of g of x is equal to x, which is also equal to g of f of x, which is equal to x, this is a function. (27) Use the graph of the function f of x to state the following information. So I have this graph right here, and if you can't see, this is all like solid line. So this is a solid line. I'm not going to draw over it. But you know that these are all solid lines and these are all closed circles. It's kind of hard to see in the picture, but in this example, all of these are closed circles. Alright, so tell the domain and tell the range. So we know that the graph, like from left to right, there's no holes between them. So I can write this as an interval notation. Even if there were holes, I could write it as interval notation, but for this sake, I will just use interval notation once. So my lowest point, remember that when I write interval notation, it's like parentheses or bracket, small and large and close, or like this, or even like this, or like this. Doesn't matter, but my small and large are still going to be the values inside. And I know that all of these are solid dots, right? So I'm going to use the closed brackets only. So I'm going to use bracket. My smallest value is 4, or -4, sorry. So -4. And my largest x value is +4. But what about my range? What is my lowest point in my graph? I know my lowest point is -2. -2. And I know that my highest point is not 4, but is actually 5, which is right here. So 5. Nice. Sketch the inverse of the same graph. So, I don't know why I used that area, so I'm gonna actually erase this. 7.5. I'm gonna erase all this. Alright, I lesson specs, you're fine. 2.5 again. Alright, sketch the inverse of the graph. So first I need to list out my original values as a table. And if you remember this from 1.3, we listed out the regular, like the original or like the base function, and then we flip the x and the y. So this right here is -4, -1. This is -2, -2, -2. This is 0, 4. Oh, my box is not too, or my table is not big enough. This is 2, 2. And this is, wait, what is this? 1, 2, 3, 4, 5. This is 3, 2. And then this is 4, 5. That means that when I do my inverse, which I will draw over here, I guess, because I don't have any space. I'll use this area right here. Yes, and I know it's hot dog style, but you'll be okay. So I had 1, 2, 3, 4, 5 lines. 1, 2, 3, 4, 5. Okay. So all I gotta do is I gotta switch my x's and my y's. So if I use like this color as my y's, right? These blue numbers I'm circling are gonna be your new x. If I consider the rule, my x turns into y and my y turns into x. So my y turns into x. So I can just copy and paste it like this. My x values will look like so. My orange values right here. -4, -2, 0, 2, 3, 4. And now all you gotta do is plot them. I used white. I'll use like this nice dark seaweed color. -1, -4. -2, -2, which is here. 4, 0. 2, 2. 2, 3. 5, 4. And if you want to draw the line, you can, which I will. -1, 4 to here to this point to 4, 0, which is like here. Then this point to 2, 2, which will be like here, then here, then here, like so. All right, so this is my new graph. Then state the domain and range of the inverse. So the inverse of this graph, the domain of this graph, is still going to be the exact same process. Where I know for sure they are going to be brackets because we said already all these dots are solid or closed and all of my lines are solid as well. My most smallest domain or x value is -2. My greatest x value is actually +5. And if you notice something, you know that your domain and your range are similar whenever you take the inverse because of our inverse rule. We know that our range is going to become our domain and our domain is going to be our range. So even if I don't look at this graph right here, I can already tell that's going to be -4, 4. And to check my work, my lowest point is 4 and my highest point is 4. Is this inverse a function? Is the inverse a function if I do the vertical line test? That is a no. Because even if I don't do the points, like if I do the vertical line test here, I know that these 2 points right here are going to be failing the vertical line test. So this is actually a no. And you can always write vertical line test as your explanation. Because I already showed in the picture that the vertical line test is failed in this picture. So it's a visual aid. So discuss similarities and differences between functions and relations. And functions and relations, you can tell by this picture, every function is a relation. So I could write that. Every function is a relation. You could also write that relations and functions, because they're the same thing, I can write all the properties of a relation, which are 2 or more order pairs. But relations versus function, we know that functions have a bigger constriction since they are in the smaller circle, like within relations. And that constriction is the vertical line test, which means no repeating x values. So really the key point of this is that every function is a relation, but we know that functions have a limitation, and that limit is that you cannot have repeating x values. That's the main point of that. And to our last page, we're going to be talking about the properties. And the properties of inverse functions, which are pretty much what we talked about in 1.3, or no, 1.4, sorry. But this was really showed in all of our unit, really. The property f of -1, which is the inverse of f of x of the function, is not always a function itself. This only occurs when the original function f of x is 1 to 1. So 1 to 1 means that your 1 to 1 is like having like your x value and your y value, and those two are original. As in, if I have 2, 3, then I can't use 2 ever again. I can't use 3 ever again. So I can use 3, 4, and then 4, 5. Cannot use x more than once, and you cannot use y more than once. The domain and range of a function f of x are reversed in the inverse function of f. If f of a is equal to b, then inverse of f of b is equal to a. If AB is a point of the graph of f of x, then BA is the point of the graph f of -1 of x, which is also known as inverse of f of x. So your x values, your xy becomes your yx. That's pretty much all they're saying in this paragraph right here, and we showed it to you in previous pages. Like, for example, what the? Did I do this page? Whoops. For example, I didn't. Let's see here. Like here, my x's and my y's switched right here. So I know that this rule applies to all my inverses. So to abbreviate, switch x to y and y to x. These are original and these are inverse. This is really bad. Inverse. The inverse of x is a reflection over the y equals x line. And I've shown to you this already in class whatsoever, but just know that this applies, and it is true. You can solve by the inverse equation of a function by switching x and y of the original value and solving for y. Like, for example, f of x is 2x plus 3. Find the expression of this. So what I have to do is really just switch my variables. Y equals 2x plus 3. And if I make this into blue and I make my x orange, then really what happens is that x is equal to 2y plus 3. And then I just solve for y, which looks like this. I subtract 3 on both sides. So x minus 3 is equal to 2y. Then I divide by 2. So this is going to equal to x minus 3 divided by 2 is equal to y. The key step is here, where we have to switch our x and our y before we start solving. And the last one. F of x and the inverse of f of x are inverses only if your f of g of x is equal to your g of f of x, or your g of x is equal to your f of g of x. So we have to use function composition. And you can do this problem or not. I'll do, yeah, I'm gonna do, I'm not gonna do a problem. Okay, I'll do this problem. So for this, we have to split this, right? F of g of x and g of f of x. So I know that this video is going too long, so I'm going to do this fast. F of x is equal to 1/3 x plus 2. Then this is going to turn into f of g of x is equal to 1/3 3x minus 6 plus 2. Then I'm going to distribute. So this is 3 over 2. Wait, that's not 2. That's not a half. This is a third. So this is x minus 2 plus 2, which is equal to x. And this is true. And this is f of g of x. If I do this side really quickly, I have to write my first equation, or my outside equation, which is 3x minus 6. Then I put in this x for f of x. And I'm going to just do that really quickly, which is like so. Then I distribute, which is x plus 6 minus 6. Then it's x, which is g of f of x. So this is true. So these are functions, or these are inverse of each other. Nice. My pencil freaked out right here. Looks ugly. There we go. There we go. Okay. I skipped a page, unfortunately, so I'll do this page now, and I'll just do the left side. Let f of x equal 5x minus 2. Let g of x equal x squared plus 1. Find the value of each equation. So I have this function composition one. So this is f of g of x, and I know I can draw these arrows right here. So I start with my outside, which is 5x minus 2 is equal to f of x. Then I have f of g of x is equal to 5 x squared plus 1 minus 2. Then I distribute 5x squared plus 5 minus 2. Then this is 5x squared plus 3 is equal to f of g of x. So in review, step 1, replace outside, or not replace, outside equation. Step 2, replace x 4 into inside equation. Then step 3, simplify. Inverse function. For each function, f, find the inverse and state the domain and range of the inverse using interval notation. So if I want to find the inverse of this equation, really I have to rewrite this as not f of x but y, and I have to use my colors, which is y is orange and x is blue. It doesn't matter which colors are which. You really need to just stay consistent by switching them and leaving the color with the color. As in, like, I don't bring anything that's written in black. Like so. But now I can drop my colors because I did this correctly. And I can move the 7. So x minus 7 is equal to negative 3y. And divide by negative 3. So y is going to equal x minus 7 divided by 3, and then I can put this all in negative. Or I can just do this. Boop. Or I can do this. Boop. Whichever one. Whichever one, it doesn't matter. And this one. So my y, if I do the same principle where my y was orange, and my x was this nice blue color, that means all I gotta do is switch them. And I'm just gonna write my black ones just ahead of time because I didn't want to switch my colors, because you know it takes forever. And bada bing, bada boom. I did it. I switched my x and my y successfully. And now all I gotta do is get my y alone. And I'm gonna do that by squaring first. So x squared is equal to y minus 9. Then I'm gonna add 9 on both sides. X squared plus 9 is equal to y. And that's it. Nice. And that concludes our review for topic 1. I didn't do the right side, or like half of the questions, majority half of the questions, because I wanted you to try it out yourself. If you have any questions, please let me know in class before the test. Obviously, I cannot help you during the test. And I'll see you guys in class. See ya. Bye-bye.